So we have Melvyn Davies. I will make a usual presentation. I don't think I have to introduce you, Melvyn. And he's going to talk about Hypervelocity stars ejected from the kinetic center.
Okay, thanks, pal. I'm not going to use a microphone, but hopefully everyone can hear me. If you don't catch what I say, please shout and let me know. So I'm going to talk about hypervelocity stars ejected from the galactic center, and we already heard a little bit about this earlier. The idea then was suggested really by Jack Hills in 1988, really quite a prescient paper, and the idea is the following. So we have a binary encountering the central black hole. Black hole is here, a binary star system comes in, it gets close to the central black hole, it gets sufficiently close that the tidal field of the black hole breaks up the binary. We capture one of the two stars in the binary and we eject the other at very high speeds. It's worth reflecting actually a little bit of how that actually works, right? Because it's perhaps not obvious to everyone why we get something ejected at very high speeds. And I'm going to give a very simple explanation here, which actually hopefully will give us some insight. So the first thing to realize is the following things here. It's a little bit busy plot. The orbital speed within the binary, and we're going to compare that then to the velocity of the binary as the whole binary zooms around the black hole. So the first thing then is the orbital speed just given by this expression here. M1, M2 are the mass of the stars. A bin is the separation in the binary. And putting that in sensible units, which are neither SI or CGS, we get a sort of speeds of order 100 kilometers a second. So the two stars in a reasonably tight binary, the sorts of binaries we're interested in, are moving around at order 100 kilometers a second or so, depending exactly on the masses and the separation, of course. The tidal splitting radius, so the distance the binary has to come towards the black hole in order to be split, is given roughly by this expression with perhaps a prefactor here of order of a few. The tidal distance is the size of the binary times the ratio of the black hole mass divided by the binary mass to the cube root. So this is of order 100 here, roughly, right? If the black hole mass is a few million solar masses and the binary is a few solar masses, then a cube root of a million is 100. So the separation when we split the binary is about 100 times the size of the binary, give or take. Now, if you go through a little bit of algebra and work out the velocity of the whole binary, the center of mass of the binary as it zooms past the black hole, at that distance, when it would get split, that gives you this expression here. And it turns out then, you can do a little bit of algebra here, that the ratio between the velocity of the whole binary and the speed of the stars within the binary is given by the ratio of the cube root of the black hole mass and the binary mass. And the important point here is this factor here is large, so that the speed of the binary as it zooms by the black hole, the center of mass velocity, is much higher than the motion of the stars within the binary itself. This comes out to be thousands as opposed to hundreds. So how does that help you then? I have a very simple picture here. Yes, I couldn't draw a parabola very well last night, so I have an ellipse that just appears off the top here. But the idea here is that here's the binary coming down, here's our black hole, and here's the two stars in the binary. We're not to scale here again because this distance would be 100th of this distance, but it's easier to see. And let's imagine in this very simple picture that my binary is going around this way, so that this star is heading this way a bit, and this star is heading that way a bit in its frame, okay, in the rest frame of the binary. So that means that this star is traveling at VCM minus some v, this one is traveling at VCM plus some v. There's factors of 2 here floating around, but you get the general idea. And then the point is, this binary is broken up by the tidal field of the black hole, and so this star has a speed greater than VCM, so it's unbound. It's going to go flying off. And this star has a speed less than VCM, so it's going to be bound, right? If this came on a parabolic encounter at VCM here, then the escape speed is VCM, and so this one is bound and this one is unbound. The point is it's actually very unbound because the energy it has, the excess energy, is VCM plus V all squared minus VCM squared, right? Within a factor of 2, kinetic energy is half mv squared. But the extra energy is this squared minus VCM squared. And so the point is then our big win here is that VCM is much larger than V. So if you think about it, algebra in your head, VCM plus V squared minus VCM squared, the leading term then has a VCM times a V, right? And so this then is really quite large. And if you do a bit of algebra again, you can work out the ejection speed here, and it turns out that this is sort of roughly 10 times the speed within the binary. So the speed within the binary was order 100 kilometers a second. This V eject, the V at infinity, is of order 1,000 kilometers a second. So that's a sort of very simple picture to understand what's going on. In detail, one can do numerical experiments. Jack Hills actually in 1988 did numerical experiments, just threw in various binaries into black holes and measured the speeds of escape. Bromley et al. In 2006 did the same thing again, and they actually produced a fitting formula, this horrible-looking fifth-order polynomial here. So basically, if we ignore this for a second, the ejection speed, again, is of order 1,000 kilometers a second, depending on the properties of the binary, the mass of the stars in the binary, and the mass of the black hole, times its FR, and FR is just simply a fitting formula for their numerically achieved results. This thing contains lots of terms that don't really matter very much. Basically, this is of order unity. It's just a term to fit the numerical results they obtain. There's no science in this particularly other than just a fit to the numerical results. The bottom line is you get of order 1,000 kilometers a second, depending what these are. The D here, I should explain in this term here, is simply a measure of how close we get to the black hole. And what they actually find experimentally, if you will, numerically on a computer, is the probability of ejecting a star when you throw the binary into the black hole is a function of this penetration parameter D, given by this term here. And in fact, D goes, there's an ejection probability is 1 if you're very close, in other words, you always break up the binary, always eject. And as we have progressively larger and larger minimum distances, when we get to about 175 in this form of D, the probability of an ejection goes to 0, and it goes pretty linearly. Okay? So in other words, we can throw binaries at the black hole and work out the probability of ejecting them this way and use this formula to sort of in a Monte Carlo way produce a spectrum of ejected stars.
Yeah, so the way you describe it is like just geometrical, but there's also this, I'm just curious, there's also an argument in three-body interaction in general that you take the coefficient of energy and you eject the smallest object. Is that true also?
So, okay, so the first thing is if you have three roughly equal mass objects and two of them are in a binary and a third object comes along, if the binary is what is called hard, namely that the binding energy here is larger and more negative than the kinetic energy coming in, then we'll have something complicated happen and a star is then ejected, one of the three stars, and we're left with a more tightly bound binary. And what we find when the three roughly equal mass stars come in, this picture, that the one that's least massive is the one that's always ejected, and the binary is always left slightly more bound. But the complication in here is what's found here is that actually the star that's ejected, if we just go back a second to this picture, the one that's actually escaping here can actually sometimes be the more massive star. If the mass ratio is very different, it can actually be the more massive star. People's explanations of that vary enormously. Cole Miller has a really good explanation of that, and he's not here right now, but he'll be here next week. But his argument is that if you've got a very low mass star, then it's moving around more, and it can more likely end up close to the black hole, if you think about it. Because if we have a mass ratio that's extreme in our binary coming in, we have a very massive star and a low mass star. It's the low mass star that's doing most of the motion. And so it tends to get close to the black hole more often. And so often what we actually find is if the mass ratio here is extreme, it's actually the more massive star that gets ejected for these extreme mass ratios. Sorry, Kurt, yeah.
In the algebra, I think this came after that. We're assuming that the speed coming in that's parabolic or
sorry, yes. That's, yeah, well, it's greater than here because that's right. If it was on a circular order, it'd be 1 here. If it's parabolic, it'd be 2 here, of course. That's right. Yeah. So when I work out this number here, that's right.
Oh, let's see. I thought somewhere along the line you're assuming that it's basically parabolic on a circular order. Is that not true?
In my picture here later, yes. So yeah, so here I essentially do when I gave you the number they're working out. That's right.
But to get the right, if it were a circular orbit, I think it seems to me it wouldn't become unbound. Is that right?
I think that's right, actually. Yeah. So really, in a sense, it could be somewhat bound, but essentially this is really going to be a 2 here, and then exactly so. So then we assume here that VCM is exactly the escape speed. That's right.
Okay, and then in the next page, are you assuming at the beginning you get this formula that there's a range of eccentricities, or are you assuming basically eccentricity 1?
I believe in these we should check. I think this has a range of eccentricities in here. That's a good question. I don't recall the complete answer, so but we should check. But I think they do include that.
So, okay, unless they give a range, it would be not very realistic.
No, that's right. That's why I think they do include a range of eccentricities. But we can check after the talk. Okay, sorry. So anyway, so you're now equipped then So Jack really did in 1988, he worked all this out numerically, understood it, and made a prediction that we would get these very high velocity stars. Okay, and so now we're going to do science by ADS citations, which is this following plot. This is from this is the citations to Hills's 88 paper as a function of publication year, so papers citing him, number of papers versus year. So Jack wrote his paper in 1988, and we can see, just without knowing any science, that something interesting happened in 2005, right? Because the paper rumbles along with a few citations, and suddenly in 2005, bang, and he's now clocking 20, 25, 30 citations a year. So something happened in 2005, and we already heard about that. Sorry, this is, for those not familiar, this is Astrophysical Data Service. This is the one the astronomers always use. And the yellow is conference proceedings, and I'm not quite sure what colour to call this, is referee publications. It's a bit of fun, but the main point, the serious point, is that Jack made a prediction a long time ago, and not a lot happened observationally until 2005, and there's been an awful lot of activity since. So what did happen in 2005? You're not, hopefully, well, you can see a little bit. Don't try and read all of this. So what happened is that Warren Brown et al. Discovered, what it says here, discovered an unbound hypervelocity star in the Milky Way halo. So actually, it's quite a good example. They weren't looking particularly for these objects, right? What they were trying to do was look in the halo of our galaxy and try and measure motions of stars in the halo of our galaxy, and understanding how far away in the halo they were, probing the structure of the dark matter halo in our galaxy. That's what they were trying to do. The reason they were looking for blue stars, though, is a little bit complicated. If Kurt remembers, the one thing you had to remember from yesterday's talk, for those who were here, is that blue horizontal branch stars were horizontal in an HR diagram, which meant they all had roughly the same luminosity. So what you can do is look at blue horizontal branch stars. So blue horizontal branch stars, to remind everyone, are most often very low mass stars where you have core helium burning after that first giant phase. So if you look out in the halo of our galaxy, so imagine that the disk of our galaxy is the plane of this floor. So you can imagine most young stars, massive stars, are formed in the disk, but sort of spheroidally around all of that, there's a population of low mass stars. Okay, and by looking at their motions, you can probe the distribution of the dark matter we know is in there. So they were looking for blue stars in this halo. So they were looking up from the disk of the galaxy upwards, looking for blue stars. And when they find blue stars, we're measuring their velocities to probe this. And if they find these blue horizontal branch stars, because they know how bright they really are, they can get a good idea how far away they are. Because again, the horizontalness means they all have roughly the same luminosity, right? Because if I'm an HR diagram, I'm luminosity and temperature going the wrong way, and so the horizontalness means they all have the same luminosity. So you can get the distances reasonably easily, and you can probe it, okay? And so they were looking for blue horizontal branch stars that should be doing that. And what they found is then they take the spectrum to measure the speeds, and they found the following. So this is, I should caution, this is the VRF is a complicated thing. What they're doing is they're standing on the Earth, looking up at these stars, and when they see a star, they can measure its line of sight velocity, right? The radial velocity with respect to the sun, right? And what they can then do is work out the value of that component of the velocity in the rest frame of the galaxy. Okay? So it's not the velocity of the star, and it's not even the velocity of the star away from us anymore. This is put into the rest frame of the galaxy. So, and what you see then is loads of, in his paper, Brown et al. 2005, when they discovered the hypervelocity one, they looked at, I forget the number, it's like 20 or 30 blue stars here, something like that, you can count them up. And so most of them were in the halo. So the halo would expect to have a distribution based around 0 here, with a width here of perhaps about 200 kilometers a second. So stars are moving around in our halo at order of a few hundred kilometers a second. And so they see that, but then there's this one outlier here zipping away at over 700 kilometers a second. So by a fluke, they'd found this object. They weren't looking for these objects. What they really were is looking for these things to probe the halo of the galaxy, because these are low-mass blue stars that are just out in the halo, right? They're just orbiting around, and they go through this horizontal branch phase for a while. And these, again, are low-mass old stars. And so this is something different. This was interesting. Okay, so having discovered one, they worked a bit harder and kept looking for these things. Don't try and write all these down. I can give you them later. But you can also find them on the web, of course. But the point here is there's been several observational studies since then, and progressively over time. So the first 2 or 3 here find individual high-velocity stars called HVS 1, 2, and 3, etc. But by the time we get down to Brown et al. 2007A here, they're actually doing a survey and they're finding several objects, okay? And we're going to actually use the Brown et al. 2007A paper information, their data, in what I'm going to present in a moment. So they really are sort of surveying now, and now the total number that they see of high-velocity objects is sort of order, I guess, 20 or something towards that sort of number. Okay, so we actually did some work on this with a guy named Carl Svensson, who was then a master's student of mine, who's now a PhD student in Warwick, working with Andrew Levan on gamma ray bursts. But his work with me was the following, also with Ross Church, was to answer this question. Okay, this question means, are these hypervelocity stars blue horizontal branch stars, or are they moderately massive main sequence stars? Okay, so I'll quantify this bit first, just to be clear. These are blue stars, right? You look and you see the color of them. If they're on the main sequence, the mass of these stars is massive if you're used to very low mass stars, but is low mass if you're used to talking about supernovae. So to quantify, the mass of these stars we're talking about is somewhere around 3 or 4 solar masses. So if they're on the main sequence, they have masses of 3 or 4 solar masses. If they're blue horizontal branch, again, they look the same, they have the same color, roughly. They look rather similar, but if they're on the horizontal branch here, they could be much lower mass stars. Again, these are core helium-burning stars. And the key point here is these could be very low mass stars and could be much older. So it's very important to understand whether they're lots of low mass old things going through a short-lived phase, or are they relatively more massive and relatively shorter-lived main sequence stars.
Can you distinguish by spectrum?
So not really. What they take, the radial velocity spectrum to measure the velocities, no. You really need to do something else to differentiate here. So let me tell you what we did. Okay.
You could distinguish by spectrum if it were a very bright star, and you had enough, and you had a giant telescope with enough photons to get a very high dispersion spectrum, because individual spectral lines would show different broadening line profiles.
Yeah.
But that would be much brighter object.
Yeah, that's right. Yeah, because you could probe you can probe the surface gravity of the star, but you can't do that so easily with these. Okay, so let me just sort of explain then the Brown data, and then I'll tell you what we did. So this is the Brown data then from Brown et al. 2007A. So this is this projection here is the galaxy. So the galaxy disk lies in the plane here, okay, and then the north and the south galactic pole. So looking straight up is there, and straight down is there. And the first point to remind everyone again is when you see these coloured dots is one of their observations. So they look using what's called the Sloan Digital Sky Survey, which is photometric imaging. They look for blue things, and again, you're interested in looking for blue things above and below the disk of the galaxy. Now, the first important point to make about this, it's kind of like looking for asteroids landing on the Earth, right? I always used to explain that in my Astro 1 course. You go to Antarctica because you're walking along, you see a rock in the snow, and it's easy to find, okay? You don't look for them on a beach of gravel, right? In the same way here, they're quite deliberately looking for blue stars up here or down here because they're unusual. Because most halo stars are old, low-mass stars, and they're mostly on the main sequence, and so they are not these blue stars, okay? It does not mean that we're not ejecting hypervelocity stars in the plane, right? There's no preferred direction necessarily. It's just simply that in these surveys, you're looking for blue stars where blue stars are unusual, because they're easy to find. If you were to do a survey for blueness in the disk of the galaxy, that would be a really bad idea, because A, you've got to go through lots of dust and gas, but B, you'll find lots of young star-forming regions, like Orion and stuff. Okay, so each of these is one of their objects. They look at several hundred objects here, and they take the spectrum, and then they get the radial velocities. And so now this is their latest thing. You can see now we have many more objects. There's 60 objects up here. So it's the same idea as their first paper. They're measuring this rest frame velocity against the radial component, the component between the sun and the star, boosted into the frame of the galaxy, so taking the rotation velocity of the sun out. And you see a very similar thing to before. You see a nice distribution here. Okay, the first object, HVS1, is this one here, just over 700 kilometers a second. In between this paper and the first discovery, there's all these others, HVS4 and 5 and 6 are there. And this paper really talks about the slightly lower velocities. They were interested in were any of these hypervelocity stars were bound rather than being unbound. This star, I should explain, is unbound if you do a reasonable model for the galaxy. And so there's actually not labeled here, but there's 11 objects. You can see 11 here, an arrow, to the right of this number here. So they sort of pick a cut here somewhere, and then these are the excess. You can see this is the excess over a nice sort of Gaussian here. And so they argue that these 11 objects here are unusual, and there's also one here to the left. Okay? Remember the one to the left. The one to the left has a negative VRF, which means it's coming towards us. These being positive over here means that they're moving away from us, right? So we stand here on the Earth looking up, the stars are moving away from us, but one object here is moving towards us. Okay, you can't read this, but this is just the table of the data. So you've got positions in the galaxy, you've got this velocity here, and the velocities are typically about 300 kilometers a second. There's spectral types, which is about the color, what are called late B or early A stars. So if they were main sequence stars, that would be around 3 or 4 solar masses. And these are the distances. There's 2 columns here because, crucially, if it's a horizontal branch star or a main sequence star, they have different luminosities, so the distance will be different inferred given the apparent brightness.
Probably worth mentioning that we don't really know that they are moving on a radial trajectory away from the galactic center. We only see them from the Earth.
No, that's right. That's right. So this VRF, as I said, is the component of the velocity in the line joining the star to the sun. That's right. Okay. But we can do something rather useful, I think, is the following. Let's suppose they are coming from the center of the galaxy. So that HVS1 is really zipping away. Or it actually turns out it's almost exactly overhead, and it's traveling so fast that it's really implausible to say it's coming from anywhere else than the center of the galaxy. But let's suppose the following. Let's say, okay, let's imagine now, I'm going to make Professor Schutz here, he's going to be an observational astronomer, and I'm a high-velocity star flying away from a very high speed. Okay? He measures my radial velocity, as I will call it, radial meaning in his line of sight, blinking. But I have in reality a proper motion. I'm moving sideways or up and down, right? And you can't measure that, right? Potentially, over time, with better astrometry, maybe people could measure them, but we don't know what those are. So we have 2 unseen components, right? And I can have any arbitrary orthogonal set I could define, but I have basically 2 components of velocity that he doesn't know. But let's imagine we say, okay, let's say, well, we sort of know, or we think we know, that these objects come from the center of the galaxy. So let's add 2 components, right? So add my 2 components, and Kurt writes a computer program, and he adds the 2 components, and then he integrates me backwards in time and sees where I go, right? So if I have the wrong kind of components, maybe I go flying off and zoom past the Earth, and I play the game of adding those unseen components to see if I can get me going backwards in time to go through the center of the galaxy. Okay? So we did that. We added the proper motion and integrated backwards and, for a set of proper motions to see what the minimum distance was. And that's hard to show graphically. Hopefully this conveys some of the idea. This is one of the stars, okay? It doesn't matter. This is just one of those high-velocity stars from the 2007 paper with a velocity of about 300 kilometers a second. What I show here is a bit complicated. This is basically the components of the proper motion in very funny units. So it's milli-arc seconds per year, but that turns out to be a useful measurement units people use here. And these are 2 components, right? It doesn't really matter what these are. These are actually RA and DEC, which is just a coordinate system. The idea is I have just 2 components of proper motion. And what we have here, sort of poor man's contours, is the different symbols denote relatively different nearness to the galactic center. So the circle in the middle here, anything within that circle gets within 10 parsecs of the galactic center. So the point of this plot to take away is not what the numbers are here, anything to do with that. It's simply that, yes, for one of these velocities, given a star, we can add the perpendicular components and we find, for all those moving away, a unique solution that takes us through the galactic center. Okay, and the numbers are reasonable. I mean, it's not so surprising this, but it does help us. Okay, so we can integrate backwards and figure out the unseen components. So then we have everything, in a sense. We have the radial velocity, the unseen components we add, so we have a trajectory for a star that goes through the galactic center. Okay, so that's what I've just said. And the other important point here is given that I know everything, I know all the velocities, I can work out also through the galactic potential model whether the star is bound or not. Because again, the latest numbers, these are relatively low velocity stars. They're 300 kilometers a second, so some may be bound and some may be unbound. Okay, do not try and read all of this. This is from our paper. The point is here are all the stars. These are the ones from the 2007A. So this is the 11 I pointed out. In fact, I think there's extra one here. But it's the ones that are relatively moderate velocities on the right-hand edge of the Gaussian, those plus 11. And so what we have then, for each of the objects, we have, if it's a main sequence or blue horizontal branch, so again, there's two different solutions with different distances initially. And then we just have the proper motions we need. You don't need to read that, the distances and things. The perhaps useful things to point out here are these last two columns. The V edge here is the ejection speed, and one has to be very clear what I mean by that. It's the same thing as in that long formula that Bromley fitted to the Hills data. So V edge is the speed you have zooming away from the black hole once you've allowed for the deceleration of the black hole. So it's your initial conditions injecting the star into a galactic potential. And you can see the sorts of speeds we're talking about here are 800 kilometers a second, perhaps a little bit higher here. For our galactic model, these are unbound and these are bound. So roughly 2/3 of those 11 are bound in the potential of our galaxy. Okay, so we have, I think you can count them, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 objects that are bound. Okay, and again, we figured that out because we've gone backwards, we've worked out the proper motion to get us through the galactic center, so we have a complete trajectory. The other point I'll make is that the T edge here is the time taken to go from the center of the galaxy to where we see them today. This is in millions of years, and they're all sort of tens to 100 or perhaps 200 million years. So all of the objects we see have only been traveling away from the galactic center for something like tens or 100 million years, okay, because they're still going outwards. I did mention the one, if I go back very quickly, just to remind you, there's this one object here, which I've not talked about again, which is coming towards us, right? The 11 are here, that I've just shown that big table, that's the 11 here, but there's this one object here that has a negative VRF, so it means it's coming towards us, okay? Is this my counterexample? Is this a problem object? Okay. Well, it is a funny object because of the following, and it's going to be slightly complicated to explain this. So there's its phone number, it's its coordinate. It's the only returning star in the sample, so it's got a large but negative heliocentric radial velocity, so it's apparently coming down towards us. Okay? So the first question, is this a bound, high-velocity star returning to the galactic center? Because if it was, it'd be interesting. I mean, it's kicked out of the galactic center, it's slow down, turn around, and it's coming back, zooming towards our observer here. Okay? Well, the answer is no. And let me try and explain why we know the answer is no. Because the following happens. If I do exactly the same with this star that I did with the others, namely I'm now plunging towards Bernard, and I add, or Kurt adds, unseen proper motions to me, and he keeps doing that, and he works really hard, he maybe gives his PhD student to do it, the PhD student comes back the next day saying, no, Kurt, it doesn't work, and Kurt says, no, go back, try harder, comes back the second day, still doesn't work. The reason being is you cannot find a solution for this star coming towards Bernard by adding proper motions that take it through the galactic center. Okay, and it's kind of weird, going backwards in time. Okay, the reason is the following. If you say, okay, well, let's just go forward in time. Let's imagine this star plunging towards Bernard now. I add a proper motion just to make it go through the galactic center now. I can do that, of course, because it doesn't make sense, right? I must be able to do that, because I can just add another vector to get the right velocity to head off in any direction. And I can do that, so I can have this star heading forwards in time go through the galactic center. But if I do that, the star is unbound. The velocity I have to add is in a completely different direction. The net total velocity is so large that the star is unbound. And that's why we couldn't find a solution going backwards in time, right? Yeah? It's like you can't throw a tennis ball up and have it come raining down at twice the escape speed.
How sensitive is that to the spectral identification?
So this is true for whether it's the main sequence or blue horizontal branch star. Okay.
The only two alternatives?
Yeah, because you've got the color. So you've got, when you look at the data here, their data here, oops, you basically have, you have the coordinate in galactic scale here, and you have two distances here for these stars, depending whether it's a main sequence or a horizontal branch star. So we have that information. So what this object is...
Could I ask another question?
Sure.
You're assuming perfectly elliptical Newtonian orbits. Well, not, I mean, you're assuming orbits in a smooth galactic potential.
So, yeah, so what we're doing is... Yeah, sorry.
If this object could, if on a hypothesis that it was an ejected star that's coming back, how sensitive is this conclusion to ignorance about the potential it actually is going through, the model of the galactic potential, or maybe it encountered some massive molecular cloud somewhere?
So this thing is way out of the disk, so that the amount of stuff out there is very low.
It's way out.
I forget the distance, but all of these objects, by definition, where they're looking again, we're looking above and below the plane of the galaxy.
What's strictly ejected went through conscious.
Oh, I see what you mean.
Maybe it was deflected by a giant molecule.
But then you would need, you would have to have an incredibly strong scattering event to change the history of this thing, because it really is quite unbound. To go through the galactic center is quite unbound. And I think actually, really, when you look at it, it's a more mundane explanation, because it really is just sitting here, right? And so what this sort of shows here, the higher the value in this plot here, the stronger the statistical significance of not being a regular halo object. And so you can see for the hypervelocity stars, they're enormously above what you expect from the way extreme tail end of the Gaussian. So they're very significant. And these 11 are pretty significant too. But this object really is just at the end of the Gaussian of the regular halo. So our interpretation of this returning star is simply that it's part of the halo, just like if you looked at these objects slightly, minus 200 or minus 220. These are just regular halo objects. And when one looks at the velocities and things, one can see that, if we just say, okay, let's imagine that randomly we're seeing X fraction of its speed in our direction, just add other components that are reasonably similar in size, and integrate it in the galaxy, then you see a regular halo object. And that's what we did. Does that make sense? So in other words, we just assume we see a reasonable fraction, but not most of its speed, and add other bits, then it's a halo object. So our interpretation then is that that object is just a regular halo star. So that's very important, because it means then that we have 8 objects that are bound, that are moving outwards, and we see them all moving outwards. This will help us with the big question. So I'm going to leap around again, just to remind us what the big question was, which is whether they're blue horizontal branch stars or main sequence stars.
Wouldn't that be possible to make a concentrated effort to reach the property of this object? And under your interpretation, it cannot be a main sequence star, right?
Yes, that's right. This should not be a moderately massive main sequence star. It should be, like most of these objects, so virtually all of their blue objects they look at are blue horizontal branch stars. That's right.
Yeah.
Ooh, lots of questions. He was first, sorry. Kristen.
So one of the assumptions you have in your model too is 10 parsec target size for the galactic center. But right?
Well, so I think the point with that, what we pick is the best case in here. But it's a fair point, actually. You could ask, if we just change the conditions slightly, how different does it make it?
You could have different sizes.
Yeah. So in a sense, so the point here was to really show that you could find a unique solution. But it's certainly true that our galactic model, right, we use the Pachitsky's galactic model, which we've used before, and that the biggest uncertainty, of course, is in the very middle. But it will not change the overall gross point. So if I change my model a little bit, then the exact details of an orbit will change. But my statement about this one that's coming in being much more a halo object and not being bound if I go through the galactic center is still true.
Okay, so you think it doesn't depend on that assumption?
No, because if we change the galactic potential a little bit in the middle, of course, then...
I'm not worried about the galactic potential. I'm worried about the exact orbits.
No. So if I take an orbit with a proper motion here, as opposed to one out here somewhere, for example, it doesn't really change things a great deal.
There's a distribution of orbits. This is sort of a boom curve. Distribution of orbits, and you will disrupt at different distance from the galactic center. So you assume that if you go 10
Oh, sorry. You mean in terms of breaking up the binary?
Yes.
All we're doing right now, we've not even thought about what binary made this object, right? So all we're doing now is integrating the single star back towards the
How
galactic
about it
center.
could be 100 parsec for some very specific, loosely bound binary? Could it be bigger than the 10 parsec?
No, this is enormously big compared to the distance they have to get, right? So again, the binary has to get within a distance that's roughly 100 times the size of the binary. So if the binary is 0.1 AU, it's getting within a distance of tens of AU, typically, or perhaps 100 AU of a black hole. So they're very much closer. Sorry, the point of this plot was simply to show that we can reliably find a proper motion that gets us through the galactic center. And if I change my galactic model a little bit, the exact value of this proper motion will change a little bit, but it won't make a big difference in the overall picture of this. Kurt?
Make sure I understand something. So, since for the bound objects, what goes up must come down.
Yeah.
We'd expect, without to ignore the evolution of the horizontal branch guys, to have about 8 guys coming towards you very fast, right?
Yes.
So, the reason we don't see them is because by the time they go up and back down, they've evolved off, or...
Yes. You have evolved you have anticipated 6 slides in advance. The whole point, which we're going to come to, is the point of the paper we wrote, is exactly that. That basically, exactly, if we're all listening to Kurt, I can just repeat Kurt's talk, is exactly that point. Because these objects are bound, we have 8 objects that are bound, what we're going to now do is we're going to see one of the integrated trajectories. But the bottom line is exactly what Kurt says. What goes up must come down. If they are living forever, right, we should see as many coming down as we see going up. The forever, okay, but we can ask more than that. We can work out typically how long the coming downness timescale is, so the orbital timescale. And so if we don't see any coming down, it means that t visible, the lifetime of the thing as a visible blue thing, is less than the t coming down the t orbit, and that's where we're going to get to.
Did you consider the possibility that you have close evolved binaries which are blue, not in horizontal branch, neither?
So your
Evolved binaries which would be blue, but in neither of those cases.
So I guess then the question would be, if you had a tight binary, the picture is how you get the very high velocities. I suppose if you have a regular halo object or something. I suppose with these objects here, at least the ones that are clearly significantly different from a halo, that one, but also all of them here. These objects here, these are something that's happened to these to give them to a very high velocity. That's right. So I suppose you could imagine, for example, some exotic objects, like I could throw in a triple system to the black hole. If I have a triple with a tight binary and a looser object here, and I throw that triple at the black hole, then I could break up the triple and have a binary flying away. That's certainly possible if I have the right initial conditions, though probably that rate is significantly lower, I would think. Okay. So anyways, let's just carry on now. Kurt's given us all the bottom line, but that's fair enough. So the point then is the following, is we integrate the orbits forward in time. So to recap, we have 8 objects that are bound. We know everything about them now because we said we go backwards in time to get them to the galaxy center. So go back where they are now, but we know the proper motion. We go forward in time. And just to give you one example, there's no good way of showing this. This is a horrible plot in a way. This is one object again. It's the same object I showed the proper motions for, but they all look like this. So this is time in millions of years, so 0, age of the universe. And this is r and z. So r here is x squared plus y squared. So it's the cylindrical r, right? So it's the distance away from the center in the plane of the disk of the galaxy. The z is the one that's pointing up. You could show other kind of plots with the orbits and things like in Binary-Tremaine. Perhaps this is easier to see. So the bottom line is it's here, and it goes up and comes down, and it's going to keep doing that, right? I suppose going up and coming down is here, really. And it's doing this sort of thing, okay? And actually, it does complicated things. The bottom line is the orbital timescale is long, but not ridiculously long. It would come back again. If we look at the same object now and take the heliocentric radial velocity, so this is now the velocity we would measure, sitting on the Earth, measuring the radial velocity with respect to us, the first thing you see is all this short timescale oscillation here, which is actually the orbit of the Earth, or the Sun, rather, going around the galaxy. Okay? And on top of that, you have this trend here. Okay? And the 0 point is here. Okay? 0 radial velocity. So what you can see from this, and you can actually add it all up, but if you actually had an object that could live for 10 billion years, so if you had low-mass stars, and they were going to evolve up the giant branch, be on this horizontal branch for a while, that would happen through all time here, because some of them would be 1 solar mass stars, some would be 1.1, 0.8. It'd be going on all the time. And so you could see, perhaps from this, that on average, half of the time, if you pick a random time here, half of that time, this curve is in the negative bit here. So half of the time, you would have things coming back down on you. Okay, exactly as Kurt pointed out. That's the point, right? Okay, so the bottom line then is that we do not see any returning stars which have been ejected from the galactic center. Then, as we don't see them, we don't see any coming down, then that tells us that T-vis is less than T-orbit. That's the point, okay? So in other words, the blue stars are intermediate mass, main sequence stars, rather than blue horizontal branch stars. Okay, and we pointed this out in a paper with Carl Svensson, and at the same time, actually independently, I think one of the Brown papers mentions it and someone else, in fact. We all kind of realized this at the same time. But we were the first to actually integrate the things and check. And the key thing really is to add that proper motion to get the full trajectory and to really see it. So it seems that these are 3, 4 solar mass main sequence stars. Okay. Now I want to briefly talk about the captured star, because that's of interest to us here as well. And we had got mentioned, I think yesterday, a little bit about it. So again, we've talked a bit about this star, but what about the captured star? And the real question here is, do the captured stars give us the S stars? Just to remind everyone, the S stars, we saw a nice video of this, I think it was yesterday, wasn't it? So the S stars are these seemingly moderately massive main sequence stars, again, roughly the same mass range, roughly 3, 4, 5, 6 solar masses, perhaps some a bit more massive, seen in the center of the galaxy. Now we have to kind of remember a few units here, but perhaps I put them on here to help us. So the center of the galaxy I've taken to be exactly 8 kiloparsecs away, which means by definition 1 arc-second is exactly 8,000 AU. Okay? So, and that's 0.04 parsecs, give or take. And that's useful because these people here, this is observations, and they really put it in arc-seconds here, so an angular offset. And what we see here then is the orbits of 6 of the S-stars. We saw the video of it rather nicely, that people really see these things orbiting around. And you can see here, roughly, this is half an arc-second. So looking at that, these objects are sort of 1,000 or a few thousand AU, is their same major axes. Okay? So we need to remember a few thousand AU. I don't expect to read all of this, it's from the same paper. So this is for 6 of them. And we have here the A in arc-seconds. You can see it's 0.4, 0.1, 0.3, 0.3 roughly. Again, 1 arc-second is 8,000. And so again, we're seeing that these orbits are a few thousand AU. The other thing I'll point out is they are eccentric, the S-stars, but not horrendously eccentric. Not all of them. And that's an issue for us to remember. S1 has an eccentricity of 0.358. S2 is 0.87, 0.92, 0.9, etc. So there's a range of eccentricities, but some of them are not very eccentric. So the question then is the following, is we thought about the ejected star, but if we throw in binaries to the black hole, a range of binaries, a range of masses, a range of separations, we use the Bromley formulation to calculate in a Monte Carlo way then, you know, the kicks. We can also then, once we eject a star, because energy is conserved, we can work out the properties of the one left behind. We work out its A and its eccentricity. What does it look like? What do the captured stars look like? So this is actually that. This is a calculation we did over the summer. So this is ongoing work with a guy named Frederik Winmark, who's another master's student of mine. And this is the properties of the captured stars now. Okay, so what we have here is A in AU. So this is the same major axis of the orbits of the captured stars. And this is the eccentricity of them. And each one of these little points here is 1. And it's a Monte Carlo realization. Okay? So you make a population of binaries, you throw them in at the black hole with a range of impact parameters. Some are ejected and some are captured. Okay? And this is ongoing work, but I wouldn't take the distribution, the relative weights here perhaps so seriously, but just where they end up. Now the first thing to notice is good. We can see that you get you get orbits for the captured stars of order 1,000 or a few thousand AU. So that's good, right? That's not surprising because we knew that already in a way, because we have a certain range of separations. You go through the first calculation, you know, we tidally break it up at 100 times the size of the binary, we kick it out, etc. So one could work out these numbers. It's not surprising this, but it is actually encouraging to see that you can, you know, you capture things. The one thing I will point out, this figure was done by my summer student, but he assures me it includes all the points, and we have no system less eccentric than 0.95. So we do tend to capture them on very, very eccentric orbits, right? So these are more eccentric than the S-stars are seen to be. But people tell me, we've had discussions in the last few days, that we shouldn't worry about that too much because various scattering realizations may make them less eccentric. A very eccentric thing can become quite a bit less eccentric just by a random flick, right? So that's something to flag, that we should make sure we really quantitatively can do that we can make these things less eccentric. But nonetheless, we see an interesting range of separations. Now, I asked this question 2 years ago, and I wonder if anyone in the audience remembers what I meant by this. My question to ponder to finish off is 1 plus 2 less than 2.35? So I think I know the answer. Okay, but the point here is the following. The 2.35 refers to the salpeter mass function. So if I have a regular mass function, the dn by dm goes as m to the minus 2.35. That's a distribution of masses. It tells me that most stars are low mass and relatively few stars are high mass. The 1 plus 2 on the left here refers to binary single encounters. So in other words, I have a binary star system, 2 stars in a binary, a third star comes along. The important point here is the following. In a crowded place, soft binaries are broken up. So again, a soft binary means a binary where the binding energy in the binary is less than the kinetic energy of an incoming star. Okay? So if I'm in the galactic center and I'm not concerned about anything else other than just being a binary, I'm a binary star system in the galactic center. I'm just going to wait around forever. what will happen in the end is a single star will come along, smack. It'll have some strong encounter with me. If I'm soft, if my binding energy is less than the kinetic energy of the thing coming in, it'll be broken up. What this means then is if this process has time to happen before me as a binary scatters into the black hole and gets broken up and makes a hypervelocity star, then the binaries scattering in will be affected by this. Only hard binaries can scatter off the black hole if all the soft ones are broken up. This has two effects for us. I'll remind everyone, the binding energy of a binary is the product of the masses of the stars divided by their sum major axis, right? So if my binary contains low mass stars, I'm relatively soft and relatively vulnerable to be broken up. Or if my binary is wide, I'm relatively soft and relatively vulnerable to be broken up. So what will these effects do for us? Okay, so what I'm going to show you now, just very quickly, and I'm almost done, is a plot then, again, of calculation, just throwing in lots of binaries to the black hole. In the first calculation here, we include all binaries. So I make a reasonable population of binaries, the sort of population I would do if I was going to make, a population synthesis calculation, the solar neighborhood, a range of separations, a range of masses, the sort of things that people think are reasonable. I include all of them and throw all of them in at the black hole. Okay? So again, the relative rates may not be right here, but where they are on this distribution, where they are on this plot is correct. So the point then is if I throw all binaries at the black hole and look at the V ejected, so the speed of the hypervelocity star, versus M ejected, the mass of the star I'm ejecting, if I throw all binaries in, I get this plot. And we see something we already knew, is that most stars, then if I follow a Salpeter IMF, are low mass stars, and therefore down here, and also because they're relatively wimpy binaries and they're wide, they get broken up further out, and so their velocities are relatively modest. Lots of binaries are quite wide. Most binaries are much wider than my fiducial 0.1 AU. And so the ejection speeds here are very low, and most of the masses of the injected things are very low. Okay? Now, I've tried to make the figures the same size, and you'll see where I go wrong in a minute. So now if I say, okay, I'll make the binaries fairly hard. So I'll consider only binaries that are resilient to a solar mass 100 kilometers seconds squared amount of energy. In other words, my binary has more binding energy than the sun traveling at 100 kilometers a second. And then I find this instead. Okay? So suddenly now, I've still got some low mass objects, but all my low mass objects have very high velocities. This makes sense because if I'm in a low mass star in a binary and I'm going to get ejected, I better be closer to my companion star to be hard enough. Make sense? So if I'm a 0.1, to survive, I had to be, by definition, in a tighter binary than a 1 solar mass star. Okay? And this is the distribution we get. I'll point out, actually, with this distribution, it's not crazy, this, because if you look at a few solar masses here somewhere, you can see the range is perhaps up to 1,000. It's a few hundred to 1,000. So it's sort of the range of velocities we needed for the hypervelocity stars. If you remember, the ejection speeds we typically saw was about 800, in that calculation. So this V eject is the same V eject that I had in my table in the Svensson paper. We needed typically 800 kilometers a second for a 3 solar mass star, and that's not crazy when you look at this plot. It's sort of here somewhere. Right? Okay? Now, if I go further and make it 200 rather than 100, so I take the really hard binaries, then it goes up even further still. So if you look at that compared to that, right, again, the numbers here shouldn't represent, because in a sense we have to throw more binaries because we throw most binaries away. But the binaries that would survive in this environment then would have velocities that are perhaps even too high. So the velocities here are perhaps too high. I should caution here, I realized this morning that the units changed slightly here. That's 3,000 and that's 3,500. I hadn't spotted that before, but it doesn't change much. The bottom line here is by measuring the V ejects, we can put a limit on how hard the binaries can be. Because the binaries can't be forced to be much harder than this, because then the V ejects will be higher than the ones we measure. Already here, right, for a 3 solar mass star, it's sort of marginal whether I typically produce 800, I'd be more likely to produce HVS1. So we can place limits on the separations of the binaries being thrown at the galactic center. And that's interesting, right, because we can begin to understand a little bit about the binary population, perhaps. Okay. So just to make the point then about the ones that are captured, so this is what we just saw a minute ago. This was the eccentricity versus the A of the bound star, the star left behind around the black hole. And the plot I showed you a minute ago was this one, was actually for the hard binaries, so where I extracted or removed the soft binaries. I'll just make the point that if we're not probing softness, then I can actually make binaries that are an awful lot wider than this. Someone mentioned the other day how we're beginning to find S-like stars further out. It could be that there are much wider binaries that do not get probed by single-star scattering, and then you're left on these wider objects. It's not obvious, by the way. You might think it is obvious that all soft binaries are broken up. That's not true, because the process to scatter may not be related to having hard encounters, right? Just to remind everyone, the point of two-body scattering is that it's a lot of these things which are more important than these things, right? It's the distant encounters that accumulate to give us two-body scattering. So it's not obvious that we probe hard softness, actually. We may do, and we need to look at that in more detail. Okay. But just to make the point then, again, looking at the captured stars, my last two slides, is the A, the semi-major axis of the captured star versus the mass of it. And we can see here, if we do the hard binaries, again, binaries harder than a solar mass 100 kilometers a second squared, then you have this distribution. So we have quite a lot of low mass ones and some massive ones here. But if I go to really hard binaries, then I change it and I end up with a different mass distribution. So again, at least there's the possibility over time, if we begin to get a reasonable range of masses, to put some limits on what the initial hardness of the binaries was. Okay, let me summarize then. Hypervelocity stars are only seen traveling away from us. The one coming towards us we thought was a halo object. Then the Cutler lemma tells us that these are intermediate mass main sequence stars. What goes up must come down. We see nothing coming down, so T visible is less than T coming down, and that makes them main sequence stars. That's important, so they're 2 or 4 solar masses. The properties of them are a function of the hardness of the binaries, and this is also true for properties of the S stars, the stars that could be left behind. Thank you.